This video summarizes the deployment of one of our Arduino-based satellite remote environmental monitors configured with an autosampler to notify us when a sample has been collected from this ephemeral wash. We had some success with this deployment, but we also ran into some challenges both with the sampler as well as the REM, so this video summarizes some of the things we're doing to improve the overall design.
So you can see that we had a pretty good flow through here. Both culverts filled up. And it was strong enough to dislodge our sampling equipment. And I'm going to open up the sampler and see if we've got anything good to report. So I've gone ahead and checked bottles 1, 2, 3, and on, and unfortunately the bags are empty. I'm not sure what happened because you can see from the sampler tubing that sample was collected, that it was triggered, but the bottom line is that we do not have sample actually making it to the bottles. And I just popped the lid on the sampler, and I'm trying to see if I can retrieve any error messages, and the sampler just won't come on, at least as far as sample collection is concerned. Unfortunately, it doesn't look like we have a sample. Okay, so here you can see that there is fluid in the tube, so it's just a matter of seeing if we can drain what's been collected. And from what I can tell here, it looks like this little sampler inlet is just clogged full of sediment. So probably what happened is the autosampler just killed its battery trying to pull a sample out of this drainage. So what I'm going to do is try to jerry-rig this so that when I go up to the sampler and remove the tubing from the peristaltic pump, hopefully that will relieve the negative pressure on the fluid and it will flow into this bottle. Okay, so I disconnected the sampler tubing from the auto sampler, got a little bit of sample from there, was hoping that that would relieve pressure, negative pressure on the tubing. But apparently, considering that this is empty and this still has fluid in it, there's probably something in this line, probably sediment, that's not allowing the sample to flow into my sample bottle. Okay, so here's the problem. There's all this sediment in the line that's not letting that's not relieving negative pressure on the tubing. So what I'm going to do is try to manually work that out, and then with my other hand catch the sample in that bottle down there. Alright, so I had to take this whole thing apart, and I've slowly been working the sample out of the sampler tubing, basically just by taking the tubing and gently shaking it while I hold the other end of this tube in that bottle so that the trip isn't a total waste. Alright, so that's everything I could get out of the sampler tube. It looks like I've got about 325 milliliters. All right, we have two samples, one non-preserved, about a little over 200 milliliters, and about 100 milliliters in the nitric acid preserve for metals. So it wasn't a wasted trip after all.
So the next few slides basically summarize us trying to harden the sensor a little bit. Before it was just kind of strapped onto the bottom of the PVC, wasn't really protected. And we're also going to try to raise the sensor and the inlet tubing a little higher off the ground.
Okay, we just tested the Sat-REM. It is transmitting. I did get a signal on ThinkSpeak. John is by the auto-sampler, and I'm going to pour some water on the sensor, see if we can trigger it before we leave. All right, so here's my sensor. Here goes, John.
So overall, the deployment worked fairly well. However, we did have some challenges as far as setting things up. We had some trouble matching our auto sampler and sensor cables to the jacks on the proto board. So this next section basically summarizes some of the changes we made so that we don't run into those challenges in the future. So this is probably a little closer to what I want with respect to the proto board in my remote environmental monitor. And you can see that what I've done here is I've soldered on these female terminal headers. And you can get these for pretty cheap on eBay and then just cut them to size. And the nice thing about these is that it makes it really easy to plug in your hardware. For instance, I can take this little Pro Trinket and I can just plug it in. And approaching these deployments with this modular approach makes things a lot easier in terms of, say, wanting to replace sensors or Pro Trinkets, say with updated programs, because all you have to do is basically, pull your hardware out and then plug it back in. And the nice thing about these terminal headers is you can use wires that are color coded, and then when you have your hardware, you can basically design your plug-in wires to match whatever's on the board and help facilitate how this should actually be connected. For instance, this is the plug coming off my water sensor, and I can match the red, the black, and the white coming off the proto board to the terminal header with what should be coming off the plug for my sensor. So this kind of minimizes opportunities for errors in the field. Now you might be wondering why I went with a full-size proto board on this when the hardware I'm using only takes up half the board. Well, the nice thing about these full-size proto boards is they give me space to add an OLED screen so that I can actually see the program working via a serial terminal output from the Trinket, so that I can actually debug any problems that might be happening in the field without having this tethered up to a computer via an FTDI cable. So I've actually used the OLED displays designed for the Feather ecosystem with the Pro Trinkets. They work fine as long as you wire them up correctly. And they're very nice, they're very bright, they're excellent for field work. And it just gives me a way to make things a little bit more user-friendly when I'm in the field, thus helping me save time during setup. As far as soldering goes, all you really need to do is just basically line up these headers where you want them. And then what I do is I just wrap this with a little bit of masking tape to keep them straight. And then I can flip this thing over and solder it as necessary and get something that looks like that. So now I'll briefly go over what these terminal headers are for on this specific deployment. And just briefly, this is where my sensor is going to get plugged in, and you can see that the sensor is going to be powered off the power rail right there via the red and black jumpers. And then I also have this little lead coming off the signal wire for my water sensor hooked up to pin 3 on the Pro Trinket. And pin 3 on a Pro Trinket's an interrupt pin, so I can program the Trinket to call an interrupt function when something interesting happens with pin 3 hooked up to, say, a water sensor. For instance, I could have the interrupt function tell my satellite modem to send out a text to my cell phone. As far as this little terminal header is concerned, this is where I'm going to be plugging in my satellite modem. You can see that the satellite modem is going to be powered off the power rail. So I've got power coming off the LiPo over here. It's going through a capacitor to clean it up a little bit. And then it's going to be delivered to this rail over here. And then I'm going to have the cathode and anode coming off of the satellite modem plugged into these two sockets right here. And then of course I'll need an RX, a TX, and also a sleep pin. coming off the satellite modem and then wired to the Pro Trinket. As far as this little terminal header is concerned, this is for my auto sampler. So I'm going to have the auto sampler tied to a common ground, and then of course I'm going to need a pin to trigger the auto sampler when something interesting happens with my water sensor. And then I'll have another pin that I can use to pull the state of the auto sampler, basically to determine when the sampler program has completed. And this is the sensor that I'm going to be using. It's this little Funduino water sensor. And I don't recommend these for situations where the sensor is going to be submerged for long periods of time underwater. This stuff will just corrode right off. But for conditions such as ephemeral wash monitoring, where it will just occasionally be wetted, these work great. I've had these deployed in the field for months at a time, and they hold up pretty well. And to make things a little bit more feel-worthy, what I do is I encase them in a little bit of PVC. And that goes a long way. Of course, you can see here that I've got my color-coded cable and my leads ready to plug into my remote environmental monitor. So this works pretty well. The other nice thing about these, they're relatively cheap, of course. They only cost about 50 cents. And they also have this nice little LED that indicates that power is going to the sensor. And that's helpful when you're in the field, because one of the first things you'll probably be asking yourself if your sensor's not working is there a break in my line? Is something not hooked up properly? With these, you can immediately see if power is making it to the sensor. So that's very helpful. So now what I've done is gone ahead and plugged in the proto board with this LiPo. So I've got power going to the power rails. Of course, I've got my ground and my bat leads coming off the Pro Trinket attached to the power rail. I've got pin 3 being pulled low, which is my interrupt pin, and then I've got this wire which is going to be attached to the signal wire on my water sensor to let me know when the sensor's wet and to call that interrupt function. And the way this is currently programmed is when that interrupt function is called, it will set pin 13 high, which in turn will cause that little LED to light up, that little pin 13 LED to light up. So let's go ahead and demo this. So I've got my water sensor right here. I've got the color-coded leads, which make it really easy for me to plug this thing in the right way, so I'm not wasting time in the field. And now I can make sure that there's power going to the sensor, because there's a little light that confirms that the sensor is working, which is very helpful. And now I can go ahead and put this in a little bit of tap water and see if that light will come on. And you can see now that rising voltage signal off that white lead, which is hooked up to pin 3, is basically causing that red LED to come on. And I only have it come on for a couple seconds before I reset it. In order to light it up again, I gotta get this sensor dry. I'm just shaking it dry. And then I have to put this back in again. And there's my rising voltage causing the LED to come on. So I'll include a copy of the sketch for doing this kind of a test in the description of this video. This is one way of doing it. You don't have to use interrupt pins to detect presence absence of moisture, but it's worked okay for me so far. If you're in situations where the TDS of your water is very low, the total dissolved solids for your water is very low, and it doesn't conduct very well, you may want to come up with a different approach for running a function that does something interesting. The reason being that the signal that comes off the sensor has to be at least 1.5 volts to trigger that interrupt pin and the associated interrupt function. If you're using a very low TDS water, such as mineral water that you might have in your canteen, that may not work because the TDS is too low, the conductivity isn't high enough, and you're not getting a strong enough signal to actually trigger that interrupt pin. So I've had situations where I've tested my equipment in the field and it wasn't working, and then I bring it into the lab and it works, and I'm wondering what is going on. Well, the reason being that probably I was using some, a bottle of mountain spring water to test my sensor in the field. That was resulting in low TDS and not enough signal to actually trigger the interrupt pin. So one way you can check the response of your sensor is to hook up a multimeter to a common ground and the signal pin coming off your sensor. And right now you can see that the sensor's wet, so the voltage is a little under 1 volt. But if I place this in some tap water, you can see that the voltage increased to about 1.8, and that did prompt the red LED to come on the Pro Trinket. Now, as far as making cables like this that you can use to hook up your Pro Trinket to your sensors via your proto board, you start with these jumpers, these bare jumpers. They don't have any plastic connectors at the end, and you can purchase a little bag with the appropriate number of connectors at the end from Adafruit, and then you can just kind of put them together to make whatever you want, whether it be male to male or male to female or female to female like this one is right here, to make your own custom cables for connecting to your proto board, just like that. And here you can see that I've made one such cable for connecting the rock block modem to the proto board and the Pro Trinket. So what I'm going to do is match on this little male plug into the female socket. I'm going to match the colors for the cathode and anode, black and white. So having these colors right here kind of makes it hard for me to put this in backwards, which can cause problems when I'm trying to troubleshoot in the field. So that's really helpful. And then the other ends basically go where they're supposed to on the rock block modem. So I've got black, white, and gray. So these three are going to get plugged in right there. And then I've got RX and TX, which are going to be these two leads right here. So the only thing that's left to do on the proto board is essentially to run a lead from essentially the row associated with this gray wire to the sleep pin as programmed in my sketch on the Pro Trinket, and then do the same thing for the RX and TX. And I believe that RX and TX are going to A2 and A3 in my program. I need to check, and then the sleep pin is going to be hooked up to pin 4. So that's basically the way it works. So here's the soldering done to basically connect the this little female header to the Pro Trinket. You can see that I've got the sleep pin associated with my rock block going to pin 4, and then I have RX and TX going to pin A2 and A3 respectively. So everything should match color-wise. At least I didn't have any gray wire for the sleep pin, but you can see that the colors match pretty closely, and it makes it really hard to get confused in the field. Okay, so one thing I like to do after I've done my soldering is make sure that I have continuity between the sockets and the appropriate pins. So I'm going to set up those little male headers in there to make this easier to do with a continuity meter. And I've got my my multimeter set on continuity mode, and now I'm going to check. This one right here should be talking to pin A2. Let's see if that's working okay. Okay, so that looks good. This one right here should be talking to pin A3. Okay, that looks good. This one right here should be talking to pin 4. And you can see here that I don't have continuity, which means that something's either wrong with my soldering or I just plugged it into the wrong pin. And if you take a closer look at this, it is easy to kind of screw this up. If I kind of turn this, you can see that this is actually plugged into pin 5. So I have to use the solder sucker on this thing and get this thing moved over to pin 4. So it's always good practice to check continuity between all your connections. It's easier to find these mistakes here versus having your rock block modem plugged in and not being able to figure out what's going on, why it's not working. Okay, so the sleep pin has been resoldered. Let's see if it's talking to pin 4 like it's supposed to. That's better. And just for good measure, I'm just going to make sure that I have good continuity between the pins on the rock block and the pins on the Pro Trinket, since I've got all these wires and solder connections going on. It's always better to catch problems early in the process versus when you're deeper into your build and something doesn't work. So here goes. I'm going to check RX against pin A2 with my meter on continuity. That's good. Let's try TX against pin A3. That's good. And then I've got my on-off pin relative to pin 4. So that tells me that all my solder connections are good, that there's continuity, that the Pro Trinket will be able to drive the rock block through these connections as currently wired up. Okay, so we've gone ahead and we've reinstalled the revised proto board with our modular plugs. Makes setting this up a lot easier in the field. John has the auto sampler over here that we're going to go ahead and test with some water. And we've already ran this once, tested it with our water sensor, and we did get a post to the Internet of Things, which is positive. So the only missing piece now is to make sure that when we wet that sensor, that we actually get a response on the auto sampler, that it triggers. If that happens, then we're home free. Yeah, we went ahead and we reset this. Took a screenshot of what ThinkSpeak currently looks like with the start code and complete code all set to 0. John's going to get this wet. It's been sitting here for about 5 minutes. Nothing's been falsely triggered. He's going to get that thing wet. Okay, that sounds good. That's good. And now we're going to wait for that little red light to come on. It's going to take about 30 seconds. And if that light comes on, then we're home free.
Oh yes, it's ladies'
So it looks good, man. Looks like we're ready for field deployment.